All right, so this is day 2 of Unit 2. Power rule, that's your all-time favorite shortcut rule. And probably the most used rule for derivatives in calculus, because there's so many polynomials we deal with. We use it all the time. And then differentiability, that's just a fancy way of saying, can I take a derivative? Okay, that's part 2, so worry about that later. Power rule for derivatives. You know this already? Yes, from pre-cal? Yes or no? Anybody not remember it? We're still going to teach it. I just need to know, how detailed we need to go here. Okay, so we'll try to cruise through it, but stop me if we need to slow down a little bit. In our last section, we learned that the derivative is this whole thing. The derivative is this whole thing. The only difference between these two is whether we opted to use a delta x or an h. It doesn't matter. Textbooks even vary on which one they prefer. This is an amazing concept. I don't know if you find it so amazing yet, but maybe you will eventually. But obviously that could be quite tedious for f of x equals x cubed minus 7x squared plus 3x minus 12. And again, I'm not going to walk through each of these. This is just demonstrating that this would be a nightmare. And it's only a cubic, right? We should be able to handle things bigger than that. This is beautiful. I don't know. That's a strong word for what just happened there. But certainly very tedious, right? And that was just a cubic. So can you imagine trying to do that for a 5th degree or a 9th degree? No thank you. That would take forever. Fortunately, the calculus founders saw a pattern after they did a bunch of these. I think you know the pattern. So, somebody want to tell me what the derivative of 7x to the 9th plus 8x to the 6th is? I don't want to pull a popsicle stick because I don't know how well we know the shortcut. Barrett, go ahead. There you go. Yep. Bring the power down front, multiply the power down front, and decrease the power by 1. Way easier than the nonsense we did yesterday in the previous work on that page. Power rule for derivatives. So here it is in all fancy notation. Yeah. If f of x is x to the n, where n is any real number, then the derivative, f prime, is n x to the minus 1. Just put it in words here. The power multiplies to the front. So the n goes down front and decrease the power by 1. Power rule is valid for exponents which are numbers, not variables. So it doesn't work for 2 to the x. The power rule doesn't work for that. There's a derivative for that we'll learn later, but it's not the power rule. Okay, number 1. You know what? Let's pick on people, and let's pick on people one by one. Let's see here. Oh, Ryder picked a good time to go to the bathroom. Don't get him any returns. Lexi, Barrett, Helen. 3 terms, 3 voluntolds. Lexi, how about the derivative of x squared? Just the derivative of x squared.
2 to the x. Or 2 to x.
Yeah, 2x, there you go. 2x. Yes. Barrett, how about the derivative of 3x? 3, right? Because that's x to the first. The 1 comes down front, and then x to the 0 is the same thing as 1. That's kind of the long way around. Derivative is slope. The slope of 3x is just 3. So again, if you remember that derivative tells you slope, that makes that one easy. Easier, maybe. Helen, derivative of 8?
0.
Good. How did you know that? Did you just remember that? Or? Okay. Derivative of constants are 0. I suppose you could say you could do it a couple ways. That's the same thing as 8x to the 0. And so you bring the 0 down front. And 0 times anything is going to be 0. So it follows the power rule, but most people just remember that the derivative of a constant is 0. Another way to think of it is, there's y equals negative 8. Oh no. Was there any milk in that? Okay. What's the slope of y equals negative 8? What's the slope of that line? What is it? 0. And if the slope is 0, the derivative is 0. So lots of ways to remember that the derivative of a constant is 0. We don't need to write the 0. So the derivative is 2x plus 3. All right. Here's where we start asking the question in different ways. It's still the same question, but we're just wording it different. The slope of the line tangent to the graph, that's a fancy word for find a derivative. Because derivative is slope, slope is derivative. So if we ask for the slope, we're asking for the derivative. Still waiting for Ryder to come back. Emma, how about the derivative of 5x to the 9th?
45x to the power of 8.
You got it. Number 3, what is the instantaneous rate of change? That sounds fancy, but what am I asking for? What's another name for instantaneous rate of change? Derivative. So we just have to make sure we know all of these terms for derivative. Oh, this is a fun one because I can ask a whole bunch of different people. Make sure we know what's going on. Zach, Harper, Sophia, and I guess I need 2 more. Daniel, and Hector. Okay, so one at a time here. Zach, what's the derivative of negative 2x to the 7th? Yep. Harper, the derivative of 5x to the 5th? 25x to the 4th. Sophia, the derivative of negative 3x squared? Negative 6x. Daniel, the derivative of 17x? Good. And Hector, the derivative of negative 20 is 0. And of course, you don't need to put the plus 0, but I'm trying to show where all of those pieces came from. But you don't need to put the 0. Okay, number 4 suddenly gets interesting here. That d dx right there, that means take a derivative. So again, more ways to say find a derivative. Do you remember how to do these? Shortcut rule is easy when it's a nice looking polynomial. So, what do you mean bring it to the top, I guess? Yes. This one doesn't have a denominator. So, what's the same thing as the cube root of x? 1/3. So x to the 1/3. What about 5 over x cubed? How could I rewrite that? Not a derivative yet. I just want to algebra this thing first. 5x to the negative 3. And then, that one's all kinds of messed up. The 5th root of x squared in the denominator. If you can fix that one, Yes, x to the negative 2/5, right? Negative because it's in the bottom. The flower power grows on top and the root grows in the bottom. Algebra. Okay, all that was algebra. Now we get to use the power. It's still the power rule. It's just with fractions. We got to be careful. But I bet we can still handle it. I'll go with Claire and Ryder and Caden. So Claire, how about the derivative of x to the 1/3?
1/3 x to the
Close. 1/3 minus 1. We're going to start at 1/3 and subtract 1.
Negative 2/3.
There you go. Negative 2/3. Ryder?
15x to the power of -2.
If I start at negative 3 and I
To the power of...
thinking I'm visualizing a number line and I'm subtracting, so I want to go to the left.
-4.
Negative 4. I don't want to say I'm glad you made that mistake. I'm glad you made that mistake today rather than on test day. But the mistake he made was a very common mistake. You're just going fast. You're thinking about, decrease the number by 1. And then your brain isn't thinking about negatives, and so you say negative 2. So, common mistake. Glad you caught yourself. Caden, you got fractions to deal with here. You got the worst one. Sometimes just seeing it out to the side, maybe. So negative 2/5 minus 5/5 would be negative 7/5. That's kind of a yucky one. That is an okay answer. Nothing wrong with that. But we generally don't like negative exponents, so a multiple choice answer might be, let's see if I can clean this up, x to the negative, so that'd be 2/3 in the bottom, and then x to the 4th in the bottom, and then x to the 7/5 in the bottom. So that might be the multiple choice answer. So again, that difference between your choice, leave it alone, but if you're looking at multiple choice, they may fix it. Now, hopefully, if your paper says this, and then you look at your multiple choice answers and they don't look the same, you can figure out how to get to that without too much difficulty. 5, more algebra. Okay, so I can't do the derivative of the top and the derivative of the bottom. That would be really nice if that worked, but it doesn't. So, did y'all see one like this last year? Do you know what to do on this one? Barrett? Yes. I'm going to, I guess, skip a step. I'm just going to divide x squared into each of those. So 2x squared minus 3x plus 9 minus, what's this one going to become? 7 over x. Yes, but I don't want the x in the bottom. Can you skip a step for me or put it in the right format so I can take a derivative? 7x to the negative 1. And then that last one, kind of the same thing. It is 1 over x squared, but if I want to set it up to take a derivative, I want a power, not a denominator, so I'll write it as x to the negative 2. What a great day for popsicle sticks. 1, 2, 3, 4, 5. Lila, Tristan, Graham, Maddie. All right. In order, Here we go. I'll still use the right notation. It asks for dy dx. That's the same thing as y prime, but it asks for dy dx, so I'll write it like that. Lila, how about that first one? What's the derivative of 2x squared?
4x.
Tristan, the derivative of negative 3x. Good. Graham, the derivative of 9. Again, don't have to write it, but I'm going to keep writing it, at least today, in case you go back to check your notes, you'll remember where stuff comes from. Maddie, things are getting a little tricky here.
7x to the negative
Very nice. And Leah? Good. And again, a multiple choice might clean that up for some of the algebra stuff, but we're okay with that. Uh-oh. Well, there were two options. Our first answer, and then the cleaned up no negative exponent answer. Alright, that last one. I don't like that as it stands. I need to algebra that first to make it look better. Will, can you algebra that into something nicer? Meaning x with a power?
1/3.
Kind of? I mean, it is x to the 1/3 negative. Good. This is all our power rule, our negatives and fractions. Let's see. Negative 1/3 times 3 is just 1. So, the negative 4/3. That would be the preferred answer that you would like to give. But multiple choice might flip it to the bottom. Might even, let's see, the cube root of x to the 4th. I could write it like that. This would be our preferred answer, but multiple choice might do some algebra tricks to make sure you're paying attention there. But again, free response, go with the safe stuff. Okay, that's all pretty easy stuff you know already, and even if you didn't, it was pretty quick. Differentiability. Sort of like, it's like continuity in that differentiability is a condition for quite a few theorems. So we have to learn if things are differentiable, because if they're differentiable, then we can use some other stuff. So this is like one step on a longer path, if it's differentiable. A function is differentiable at a point if the derivative of the function exists at that point. Well, remember, derivative and slope are not quite interchangeable, but pretty close to it. So if you'll just remember that differentiability means, does a derivative exist, which is the same question as, does the slope exist? So we're going to sort of translate this back into algebra language, and I think that will make this easy. Because we're still new with derivatives, but we're pretty good with slope. So let's think in terms of, does the slope exist? If the slope exists, the derivative exists. If the slope doesn't exist, then there's no derivative. Remember that the derivative of the function is the slope of the tangent line. So what might be happening in the function that would make the derivative, aka slope, not exist? So can you think of examples of things where a slope wouldn't exist? Oh, this is harder than the discontinuity guessing game that we played. Think of anything where a slope would not exist?
0.
What do you mean, like a zero slope? But that's a slope equal to 0, and that's okay, if that's what you're talking about. The first one is like so simple no one even thinks about it. But if f has a discontinuity, can't be a slope at a discontinuity. Remember, discontinuities are holes, jumps, and vertical asymptotes. Right, you can't have a slope at a point if the point doesn't exist. It'd be really tough to have a slope at a point where there's, like, well, which slope would we be talking about there? And a vertical asymptote, again, there's not even a point there, so there can't be a slope there. Barrett?
Also, how would the value's not a function? Because like if there's two y values for the same x.
Oh, yeah, yes. You're right. We're assuming functions, though.
Okay.
But you're right. Yeah, if it was two values there, you wouldn't know which one to use. So it's not a function, and how would you know the slope there? Because there's two different points. So that's right. But we're going to throw that out by saying it has to be a function. Two others that you might think of. If f has the fancy word is cusp, the less fancy word is sharp turn. Something like that. Like, how am I supposed to draw a tangent line when there's a sharp point there? I don't know. Like, it turns into a teeter-totter thing instead of a tangent line. So if there's a cusp, you can't have a slope, which means you can't have a derivative. And then lastly is one you know, but it's one that people get messed up in algebra, and so sometimes your brain doesn't make it all the way to calculus with this one. This is a zero slope. What type of line has no slope or undefined slope? Yeah, so if there's a function that has a vertical tangent line, this one's a little different than the others because this one does have a tangent line, but the slope of a vertical tangent line is undefined. So if the slope is undefined, the derivative is undefined. But again, that one's a little different than the others because there's still a tangent line there, but its slope is undefined. Therefore, the derivative is undefined. So most of the time you don't have to really memorize those. If your brain connects derivative with slope and you see something and think, wait a minute, that can't even have a slope. There can't be a slope at a hole or a vertical asymptote or a cusp or a straight up and down slope, so they're not differentiable. So again, if you connect differentiability or derivative and slope in your brain, most of this stuff will follow. F has a corner at x equals a if f has a sharp turn at x equals a. That's the cusp thing. Some textbooks use the word cusp. The technical way to say it is the slope from the left is different from the slope from the right. So for this one, the left slope is positive, but the right slope is negative, so there's no slope, no derivative. Okay, so these are the things we're looking for when we're looking for things that don't have a derivative. State the value of x at which f is not differentiable given this thing. Okay, so looking back at my list, I'm looking for lots of things. Holes, jumps, asymptotes, sharp turns, and vertical tangent lines. So what's going on with number one, and where is the problem? So x equals 3 is not differentiable. That's all it asks, so that's all we have to say. Why is x equal negative 3 not differentiable? Okay, it cancels out. It's a hole. But from the continuity thing, anything from the bottom is going to be a problem for continuity, which means it's going to be a problem for differentiability. Ooh. Even before we look at the inside of that next question, what's the bars mean? Perfect. Marie, you didn't even give the name. You just like, take the V thing. This has got a quadratic inside of there, but the absolute value, that makes a V, so those are going to be cusps. Wherever the inside is 0, there's going to be a cusp, because that's where it's making some weird V thing. And I don't really know exactly what this graph looks like, but I bet they made it to where it can factor x minus 3 and x minus 2. So there are cusps at x equals 3 and x equals 2.
Are these always true for the absolute value?
Anything that makes the absolute value 0, that's not quite right. Almost anything that makes the absolute value 0 is going to be a cusp. Maybe a better way to, this is more than we really want to worry about, but the 2 and the 3 are the zeros of this thing. So there's the graph of the parabola, but if we absolute valued that and made the negative turn positive, there would be our cusp at 2 and 3. So for us, if it makes the absolute value 0, there's a cusp there. There's a few exceptions, but we're not going to worry about the exceptions for that. Number 3, find the values at which the cube root is not differentiable. Kind of two ways to do this. Do you remember what the graph of a cube root looks like? I think that's right. Emma's trying to draw it in the air. Let me give you two choices, and you tell me which of these is the cube root. I couldn't tell which one you were drawing because they look kind of similar, especially in an air graph. So which one of those is cube root? The second one. That one's x cubed. So cube root is that. Thank you, sir. So graphically, I don't know if you can see this, but there's a vertical tangent line at x equals 0. But that requires knowledge of the graph. Let's pretend we didn't know what the graph looked like. Maybe that's not such a pretend thing. So that's x to the 1/3. Let's just assume it's differentiable. So let's take a derivative, see what we get. All right, if it works, then that means it's got a derivative. So 1/3 x to the negative 2/3. What does the negative do to a, like if the exponent is negative, what's that do? What's that do to the x to the 2/3? Flips it in the bottom. But now I can't divide by 0, so x can't be 0. So it's sort of two approaches to this one. There's the graphical approach, if you know what the graph looks like, and the other approach is, well, just take a derivative and see if it works. And if it works, then it's differentiable. 4 is always a fun problem. State the values where that is not differentiable. I'm not doing that one graphically because I have no idea what that looks like. So let's just take a derivative and see what we get. Oh, let's keep picking on people. Pretty rare in calculus to get through this many. This many names. Right. Audrey, the derivative of negative 3x to the 5th.
Negative 15x to the
15x to the 4th. Elizabeth, the derivative of 3x squared.
6x.
plus x. Laura, the derivative of minus 9x.
9x to the 0. Wait, no. Is it just 9?
Yeah, I was going to say 9x to the 0 isn't wrong, but just 9 would be a little bit better answer. And Marie? 0. Again, don't need the 0, but I'm still emphasizing the piece-by-piece derivatives here. So is there any value of x that would mess this up? Is there any value of x I can't plug in? I mean, that's a polynomial, so I can put in whatever I want. So this is a bit of a trick question. This one is always differentiable. Polynomials are, like, you can use that whenever you need it. Like, that's your justification. If it's a polynomial, it's differentiable.
Why can you take the derivative of number 3 and 4 being compared to number 2?
Because I don't know how to take the derivative of an absolute value. I mean, I do, but like you don't, and I don't want to teach that. Like, I want to think about it differently. I don't want to have to do the derivative thing for that one. That would be a real pain. Number 5. Let f of x equals that thing. Which of the following statements are true? Guaranteed you'll get one like this on the test. Just go ahead and guarantee that. Which of the following statements are true? Okay, so before we look at the statements and talk specifically about like what they are, like what might be going on here? What does this look like from our last unit? What might be happening? A jump. There might be a jump here. So I'm going to need to check at 3 to see if there's a jump. And that's basically what Roman numeral 1 is saying to check. Let's check from the left and the right. If they match, then the limit exists and there's not a jump. So, let's just say left limit equals, that would be branch A. 3 plus 2 is 5. The right limit, that would be branch B. 4 times 3 minus 7. 12 minus 7 is 5. So, yeah, that limit exists, and it's 5. We're good there. F is continuous at 3. So I only need to check one more thing. Continuity is left limit equals right limit equals function value. F of 3, that would be branch A again, because that's the equal sign. We already did this. 3 plus 2 is 5. So, yep, it's continuous at x equals 3. Differentiable, now I know it's connected, but I'm like, it's a second order connection thing. Is it connected like that? Or is it connected like smoothly? So is there a cusp or is there no cusp? So I know they're connected. I've got the continuity part, but I need to know if it's a smooth connection or if it's a harsh connection. So do you have any idea how I can check to see whether the connection is smooth? Like what? Use a calculus word. What makes this connection smooth and this one not so smooth? What am I looking at there? Looking at the point, but what about the point? What makes this one a smooth connection, and this one's a connection, but it's not smooth. It's cuspy, jagged.
The slope on the left is different from the slope on the right.
Perfect. So I need to check not just the left limit and the right limit, but I need to check the left slope and the right slope to see if their slopes match up, because then I would have a smooth connection. Left slope equals right slope. So now I have to take the derivative of both pieces and check to see if their derivatives, if their slopes match up. So I'm going to just call this one A prime since I already kind of labeled it A. That derivative would be just 1. B's derivative would be 4. So what does that mean about that connection? The left slope is 1, and the right slope is 4. Yeah, those are a jagged connection. So 3 is out. 1 and 2 only.
So it's a cusp.
So that means there's a cusp there. The common mistake on that one is to, and I don't remember if the test does it or not, so I don't know if we're mess with you on this one, but to give you a problem where their slopes match, separate problem here, where their slopes match, but there's a discontinuity. So would you say that that one is differentiable at that point? Good, no. But what's going to happen if you take the left slope and the right slope? They're going to match. So be careful. You have to check continuity. You can't just jump ahead and say, I'll just check the left slope and the right slope, because we may be trying to play a trick on you where the left slope and the right slope are equal to each other, but if they don't match up, then there's no derivative there. Number 6. Graph of a function g is shown on the right. At which value of x is f continuous but not differentiable? So I want continuous but not differentiable. You know what? Let's just talk about all 5 of these points. Oh yeah, Avery's in Chicago watching a concert. Good for her. Well, Cody's not here. People recovering from the football game. Perfect. We got through everybody. So in order here, Sayla, tell me about point A. Is it continuous and is it differentiable?
I put it's continuous but not differentiable.
Good. Perfect. We'll just do a little checklist here. Continuous, yes. Not differentiable. So I think that's our answer. Let's check the others. Evan, tell me about B. Is it continuous? Is it differentiable?
I think it's continuous.
At B?
Or is it differential? Or is it neither?
Why is it neither? Other than Graham said so.
It has a hole.
It has a hole, so it's not continuous. And if it's not continuous, it's automatically not differentiable. So that one's out. Ryan, what's going on at point C?
Continuous, not differentiable? No, both.
Both. Yeah, it is continuous. It is differentiable. The slope's probably 0 there, but that's okay. We're okay with a 0 slope. Trevor, how about D? It is neither. If it's not continuous, it's automatically not differentiable. And Alec, point E? It is both. It is continuous, and it is differentiable. There is a slope right there. I don't know what it is, but it's got some slope. So continuous but not differentiable was A. Sayla was right from the get-go. Another good example of a concept question, but not a calculation question. 7's pretty similar. Let me peek ahead. Do I need to check any others? 8 is the same as 5, it's just worded differently. Let's jump down to number 9. We've got the absolute value there. Let f be the function given by absolute value of x. I don't know the derivative of the absolute value of x, but I know the shape of the absolute value of x. Show me with your arms. What's the shape of absolute value? Yep. So I don't want to take a derivative, but I know what the shape looks like, so I can probably answer all of these questions. Is it continuous at 0? Yep. Is it differentiable at 0? Why not? There's a cusp there. And, this is different, I guess. Is it defined at 0? Yeah, it's the point 0. So 1 and 3, but not differentiable. All right, so shortcut rule, and then is it differentiable, which is a fancy way for saying, is there a slope there? Yeah. It's on the shelf over there. So, worksheet 2 is today's assignment. You got through all the popsicle sticks, so that's a good day from my perspective, maybe not from your perspective. Did I call your name, Brady? Yeah. Your popsicle stick is probably still in the 4th period bin. Think I called everybody else? I was like, wait a minute. Looking over there. Called Helen. Isabel. Izzy. Isabel, Izzy.
I don't really care.
Well, pick one. Isabel. Yeah. Braden? B-R-A-Y? No Y. Yeah. That's the other reason I like to do the popsicle sticks. Just find out who doesn't have one. And I take roll. Cody and Avery. All right, have a great weekend. Good work this week. Why don't you take Monday off on me? You're welcome. Goodbye. Y'all have a good weekend. Goodbye. I know, they're rough. Try to land relatively easy stuff on days after Thursday game.
Have you checked out the math test yet? How are they looking?
They're looking okay. I'm like halfway through grading them.
Okay. Not too bad.
Not bad. Yeah.
I got home at 11:40 last night.
Thank you.
I was in bed at like 12:30.
Yeah. Michael is the same. Thank you. Have a good weekend, Brad. can't express an opinion on relative to the others. Gonna reach out and grab ya. Abracadabra. Do-do-do-do-do-do. Do-do-do. Oh, no. Still recording.